Hello everyone, welcome back to JDCodebase. This is the video number 36 of our LeetCode 75 study plan series. And today problem is the LeetCode number 437 path sum part 3. And I want to be honest with you, when I first saw this problem, I also get confused. The tree, the map, the backtrack, it felt like a lot. So in this video, I'm not going to start with a tree. I am not even going to start with the code. I am going to start with a straight line of 3 numbers. And once that clicks you, everything else will fall into place automatically. So let us get into it and let's read the problem statement first. Given the root of a binary tree and an integer target sum, return the number of paths where the sum of the value along the path equal target sum. The path does not need to start or end at the root or a leaf, but it must go downward, that is traveling from parent node to child node. So if I simplify this, we have a binary tree. We are given a target number and we need to count how many paths exist in the tree where the number along the path add up to the target. Now, two important rule about the path is the rule number 1 says it does not have to start at the root and it can start from any node. Rule number 2 says it only goes downward, means parent to child. You cannot go up. That's it. Count those paths and simple. So forget about the tree for some time. Just forget about the tree. We are not solving any tree problem right now. Start with a straight line. I have this a straight line 10, 5, 3. Just 3 number going straight down, and our target sum is the 8. I just want to know, let me wait a second. Yes. So I just want to know which group of connected number add up to 8. Let me check every single possibility. 10 alone is equal to 8? No. 10 plus 5 is the 15. It is equal to 8? No. 10 plus 5 plus 3 is the 18. It is equal to 8. No. Now I come at this position 5. Does 5 alone equal to 8? No. Now 5 plus 3 equal to 8? Yes, it is. Now increase the count by 1. It's found. And does 3 equal to 8? No. So here answer is the 1. Only one path add up to the 8. That is the path is the 5 and 3. So that is the whole problem. When we have a real tree with branches, we do the same check on every possible branch. Nothing more, nothing special, no extra code. The simple brute force approach is the start from every single node, walk down from it, check every path, and that works. But it is too slow. Means you first check 10, then 10 plus 5 plus 3, or 10 plus 5, then comes to 10 plus 5 plus 3 and nothing found, then 5 and 5 plus 3, then again 3. So it's too slow. And if the tree has 1000 nodes, now you are doing a lot of repeated work again and again. 10 plus 5 plus 3 plus 7 plus 8 means every time you go up to 10,000 nodes. We need a smarter way, and that smarter way use one simple idea is the running total. Now what is running total idea? Walk down that some straight line again, but this time keep a running total at each step. Like I have this 10, 15 and 3. Let me erase this for cleaner. Let me clean this. Now start at the top. I am saying running total. Running total initially I initialize with the value 0. Start at the top, visit the 10, and running total is now 0 plus 10 is the 10. So it's 10 value, and visit the 5. Now running total is 10 plus 5 is the 15. And now next visit the third node, and running total here is the 18. Now I am standing at the node 3, right? At this 3 position. My running total is the 18 and our target is the 8. But I ask myself one question. Is there any point above me where the running total was 18 minus 8, which is the 10? So yes, I was at the node 10. At this position, the running total was exactly 10. I just found this 10 here. So everything between that point and here add up to 8. So that is the path 5 plus 3 equal to 8 and found it. So if that earlier running total exists, we found a valid path. Means current running total minus target is equal to some earlier running total. So here, why do we use the map? In the initial in just a moment ago I said about the using of the map and the backtrack. Now why we use the map here, and what is the purpose of the map here? Now to answer that question, first, did I ever see running total 10 above me? We use a map. Means the map is just a notebook. As we walk down, we write down every running total we have seen so far. As I am at the position 10. The initial value here is the 0 and 1. Means I see the 0 and it's a 1 time at the initial time. Then I come at this 10. The running total is 10. Write in the notebook. I am seeing this 10 and it's a 1 time I only see. Only see. Now come at this 5. Running total is the 15 for this. Write in the notebook. 15 I see only 1 time. Now running total is the 18 and now check in the notebook. Note for this 3 node. Every time we have to check whether the running total minus target sum, that sum is equal to, that answer is equal is already present in our notebook or not. If it is, like here I have this running total 18. 18 minus 8, 10. Does 10 is in the notebook or not? Yes, I have this 10 in the notebook, and so increase the count plus plus by 1. Means any count plus plus. So that is all the map does here in this problem. It's just a notebook of running totals, and we start the notebook with the one entry already written, that is the 0:1. Now why? Because before we reach the first node, the running total is the 0. Initial value is the 0 here. And this handle the case where valid paths start right at the top itself. Like instead of 8, forget about the target sum 8. If problem says give me 10 and first root is the 10, so they both are equal, then count it. So that is why we have to count is 0 and start with the 0 running total with the frequency of 1. Now this is the part that confuses most people, but it is actually simple. Imagine the tree has 2 branches. Like here I have this tree. What happened? Yes, I have this tree 10, 5 and 3, 3, then again comes to 2 here, then minus 2 and 1. So this tree has a left branch and a right branch. Like when I walk down from the left branch to node 5, I write the running total as the 15. Till now the running total is the 15. Everyone knows. I just a little moment ago I just write here, and now I walk down to the right branch here, means till this minus 3. At this position, at this point, is running total 15 still valid? Means no, that is that 15 from the left branch. I am now on the right branch. They both are the different. This is the right branch, this is the left branch. They both are the different, completely different path. And if I keep 15 in the notebook, and it will give me wrong answer on the right branch. So whenever I finish with a node and go back up, I erase it running total from the notebook. That erasing is the backtrack step. Like I have a notebook. I am using for the 5. I am just count the frequencies for the left branch. for 15, then 18, then 21, and all this stuff, all these values. Now I come back at the top again after all the sum and count calculation. Now I am moving towards the right branch. Does the running total that data I store in the map in the notebook, does it really helpful in the right side of this? No. Why? Because these are the value different. These are the total different path. Then how can they the values are used in this? So that erasing is the backtrack step. Means we have to erase these all data and start a new fresh data in the right side. Now let's write the code for this. I hope you understand the basic idea, what we are saying, what this problem statement is saying, and what we have to find out. So this is the main function, the path sum. It takes the tree root and the target. Now let's write the const map is equal to new map, and set here a value map dot set 0:1. So map, our notebook, we started with the value 0:1, and it's an empty path, has running total of 0. Means this is our notebook, this map is our notebook, and the initial value is the 0:1. Now let count equal to 1. Count is equal to 0. Our this is our answer. We add to this whenever we find a valid path. Means every time whenever we see a valid path, count plus plus. Now let's define a function DFS. It's take a node and a running total. So this is our working function, a recursion function, and it take the current node and the running total so far. Like first start with the 10, then this 5 is a separate node, then this 3 is a separate node, it's this 2 is a separate node, minus 3 is a separate node. So every time it's take this type of value. Inside this, first write base case. If node is empty, then return, simply return, nothing, 0, no null value. Means we walk past a leaf, means into an empty space, like node dot left is either null, means we are reached at the leaf of the tree. Now come to the running total. I define this or not? Yes. So its running total is equal to plus is equal to node dot value. Means add the current node to the running node total. Now this is the main idea of this, main part of this code, running total minus target sum. So if it is, then count plus equal to map dot get needed, else use the 0. Means ask the notebook, did I see this running total equal to running total minus target? Means I have this 10, I have this 5, 15, I have this 18, 3, 10 plus 5 plus 3, 18. Every time I check, does means 18 minus target sum 8 is it 10. Does the map contains this 10 or not? If it is, then we have to increase the count. So this is the that count to our answer. Else means every time either it's found or not, we have to write here map dot set running total with the value map dot get running total, and if it is, then use the else use the 0 and increase it by 1. So write the today running total into the notebook. This is the every time we have to write here map dot set running total and map dot get the value. If maybe we already see that like here 3 and 3, there are the two times, so that's like. And after this we have to again call the DFS node dot left side and pass the running total, and also write here DFS node dot right side, pass the running total, means walk into the left child and pass the running total down, and after that means now everything is perfectly done. The last part here is this one, means delete the running total of the left side for when we are moving towards the right side. So for that we have to write here map dot set running total map dot get running total, and it's -1, means done with this node, erase its running total from the notebook, and this is called the backtrack. And after that this function is completely done. It's a recursive function, and call with the main root, and initial value is the 0, and in last return count. Let's run this code. And yes, it's accepted. Let's try to submit. And yes, our solution is accepted. All the test cases are passed. The whole thing in this problem is about the 4 line, only 4 line. Walk down the tree, keep a running total, and at each node, if running total minus target sum is in the notebook, then means check it. Check if it is notebook, then count plus plus, else just skip it. And running total, write the running total in the notebook by using this line number 15, and else go deeper, means erase it when done with this right node, like left side or right side, whatever. So time complexity here is the big of n, because we visit each node once, and the space complexity also big of n, the notebook and the call stack here, means the map here we use, and the recursive call stack. So that is the path sum 3, and the key idea is just the running total, walk down and keep adding. At each node ask, is there a point above me that makes the piece between us equal to target or not, and for that use a notebook to answer that in big of 1, because map searching time complexity is the big of 1 in the best case. So